This is you. You're sitting at a table trying to get some work done. You start using a pencil, but soon decide to change your mind and use a metal pen instead. At that point, you realize the pen feels much colder to touch than the pencil, even though they are the same temperature, 25 degrees Celsius. Why is this? You see, perception of temperature has to do with both temperature and the rate at which heat transfers. In this case, the apparent difference in temperature is due to different rates of heat transfer. The metal pen conducts heat away from your hands much faster than the wooden pencil because metals are better heat conductors than wood. As you can see, different rates of heat transfer have different perceivable effects in our everyday life. In this experiment, we wanted to explore this idea of perceivable differences due to different rates of heat transfer in a fun, yet familiar experiment. Here's the basic idea. We are going to fill up 3 soda cans with a little bit of water and heat them up. Once the water inside the cans boil, we are going to invert them into pans containing water of different temperatures. Let's see what happens.
So hi guys, this is how we prepare our experiment. So we are going to have 3 pans of water, each with 2 cm high of water in it. So the first pan has ice water at 0 degrees Celsius. The second one has 25 degrees Celsius water at room temperature. And the third one will be hot water at 85 degrees Celsius.
I have now 3 empty soda cans. I've already filled 2 of these with 25 milliliter of water, and I'm gonna transfer the last one.
Okay, so we're going to heat these cans up on the stove coils until the water inside them starts to vaporize. After they start to vaporize, we'll wait 15 to 20 seconds and then they will be inverted into the pans with water.
Okay, so taking a closer look at these soda cans now, we see that there's vaporization coming off the top of each can. So at this point, I'm going to now turn off the stove, and then I'm going to proceed by inverting into each one of these pans that we have here. First, I'll do the cold water at 0 degrees Celsius. Okay, see there's not a big contraction. Second, we're going to be doing the room temperature, 25 degrees Celsius. Okay, not as much as the first one. Lastly, boiling water, 85 degrees Celsius. Let's take the top off of that. And we see that there's very minimal, if any, contraction in the soda can. Just holding these up, just for comparison's sake. Again, here's 0 degrees Celsius, 25 degrees Celsius. Lastly, it's not too hot. 85 degrees Celsius. So why is there such a drastic difference between 85 degrees Celsius, 25 and 0 degrees Celsius? I'll leave that up to Prasanna to talk a little bit more about the heat transfer concepts involved with that.
So back to the drawing board. The differences in final volume of the cans can be explained by the differences in the rate of heat transfer caused by the temperature difference. First, look at why the can collapsed in 0 degrees Celsius water. The water inside the can boils and the can is filled with water vapor. As soon as we invert the can into the water vapor condenses instantaneously, creating a low pressure inside the can. At this point, the pressure outside the can is greater than the pressure inside the can, causing it to collapse. Now let's look at the 25 degrees Celsius can. The can is filled with water vapor again and is inverted. But this time the water vapor doesn't condense as quickly as the 0 degrees Celsius case. Note that this still creates a low pressure inside the can, but it happens at a slower rate. This allows water in the pan to get sucked into the can to equalize the pressure. So instead of the can collapsing completely, it only does so partially. Finally, for the 85 degrees Celsius case, the water vapor condenses into liquid water so slowly that the can doesn't collapse at all. There is still a low pressure inside the can, but instead of collapsing, the large quantity of water is sucked into the can. If you go back and watch the video again, you can see how much water is poured out of the can. To recap, the amount of collapse in each can is determined by the rate of heat transfer. In this case, the rate of heat transfer is directly correlated to temperature difference between the water vapor and the liquid water in the pan by Fourier's law. Chemical engineers use this principle of heat transfer all the time. One prime example is a heat exchanger, which is used to cool something down to a certain temperature, usually with cold water. It is crucial to determine the temperature of the water being used. If the water is too hot, the desired product will also be too hot. If the water is too cold, the product will also be too cold. But thanks to chemical engineers, we can get the product just at the right temperature.